China's new battery could replace gas stations. Engineers can't explain it. Think about the last time you pulled into a gas station. 5 minutes, maybe less, and you were back on the road with a full tank. For over a century, that 5-minute ritual has been the invisible standard every other form of energy has had to compete with. Electric cars solved almost everything else: the noise, the emissions, the maintenance, but they never solved that one number. Plug in a car and you are waiting anywhere from 20 minutes to overnight. That gap is the last real argument gas still has left. Now, a cluster of Chinese battery makers is closing that gap from 3 directions at once, and the pace of what has shipped, tested, and gone into real vehicles in just the last few months is the kind of thing that normally takes an industry a decade to sort out. If you like videos about the technology quietly reshaping the world before most people notice, hit like and subscribe so you don't miss the next one. Let's get into what's actually happening, because the story is stranger and more contested than the headlines make it sound. Why nobody solved this already? Batteries have always faced a trade-off that liquid fuel never had to deal with. Gasoline is a liquid chemical that releases its energy in a controlled burn, and you can pour a tank of it into a car in a few minutes because you are just moving liquid from one container to another. A battery has to physically move ions through a solid structure to charge, and every layer of that structure has been built around a flammable liquid electrolyte since the lithium-ion battery was commercialized in the 1990s. That liquid is what makes today's batteries vulnerable to fire, slow to charge without degrading, and weak in cold weather. Engineers have known the fix in theory for years: replace the liquid with something solid. Solid electrolytes do not catch fire the way liquid ones can. They tolerate faster charging, and they open the door to lithium metal anodes that pack far more energy into the same size cell. The problem was never the idea. The problem was that solid materials conduct ions far less easily than liquids do, and every attempt to fix that with sulfides, oxides, or polymers ran into new walls around manufacturing cost, durability, or safety. For 30 years, solid-state batteries are 5 years away was practically an industry joke. Meanwhile, China had already become the center of gravity for battery manufacturing, and companies like CATL and BYD scaled lithium iron phosphate production to a point that made batteries cheap enough for hundreds of millions of people. But cheap was not the same as fast. Even the best fast chargers still asked drivers to stand around for 10 to 20 minutes, and that was the wall nobody had broken through. The battery that isn't supposed to work yet. In April 2026, a company called Greater Bay Technology, an offshoot of the state-linked automaker GAC Group, rolled its first all-solid-state battery cells off a production line in Guangzhou's Nansha district. The company said the cells are completely free of liquid electrolytes and survived nail penetration, crushing, and thermal shock tests without catching fire or exploding, the exact failure modes that make conventional lithium-ion packs dangerous when punctured or overheated. The cells reach an energy density between 260 and 500 watt-hours per kilogram, which is close to double what a typical EV battery manages today, and they support stable fast charging at a 2 to 3 C rate, addressing the charging speed barrier that has held solid-state technology back from ever leaving the lab. The breakthrough sits on what Greater Bay calls a deep eutectic composite electrolyte, an organic-inorganic hybrid designed specifically to be manufacturable at scale rather than just achievable in a small test cell. The company has filed over 50 patents covering the process, and it says the cells have already cleared the threshold needed to move from pilot production into gigawatt-hour scale manufacturing this year. This is not one lab's solo effort either. Around the same time, the Chinese Academy of Sciences Dalian Institute of Chemical Physics published its own composite electrolyte that let a solid-state battery hold on to more than 84% of its original capacity after 350 charge cycles, and Ganfeng Lithium, the country's dominant lithium supplier, began producing what it says are the world's first 10 amp-hour solid-state cells with a 500 watt-hour per kilogram density. 3 separate teams, 3 separate approaches, converging on the same result within months of each other. That is usually the sign that a technical wall has actually cracked, not just been dented. The other approach, skip charging entirely. While one arm of the industry was racing to make batteries charge faster, another decided the real fix was to stop charging cars at all and just swap the whole battery out. NIO has been building toward this since 2018, and by early 2026, the strategy had crossed from interesting experiment into genuine infrastructure. In February 2026, the company completed its 100 millionth battery swap, delivered to a driver in Zhejiang province, with each swap taking an average of about 3 minutes, faster than most people spend at a gas pump. By May, the network had grown to 3,838 stations across China, adding roughly 40 new stations a month, and the company holds more than 2,100 patents related to charging and swapping technology, over 1,500 of them specifically on the swap mechanism itself. The company is not keeping the technology to itself. NIO has signed battery swap alliance agreements with 8 other automakers since 2023, including Chang'an, Geely, Chery, JAC, Lotus, GAC, and FAW, meaning the stations are gradually becoming shared infrastructure rather than a single brand's perk. For 2026, the company's stated plan is to build 1,000 additional stations, expand its long-distance power journey routes to 100, and open a new swap route along the Silk Road, on top of a broader county-level coverage push that CEO William Li says should reach nearly the entire country within about 2 years. It is a completely different bet than the solid-state race. One path tries to make the battery itself charge as fast as a fill-up. The other assumes charging speed doesn't matter if you never have to wait for a charge at all. You just trade your empty pack for a full one and drive off. A third contender nobody expected, sodium. Just as the solid-state and swap stories were accelerating, CATL, the largest battery maker on Earth, introduced a battery chemistry that skips lithium entirely. At its Tech Day event in April 2026, CATL announced its sodium-ion battery, branded Naxtra, would enter mass production by 2026, after the company said it had resolved 4 major manufacturing hurdles, including moisture control and anode stability, that had blocked commercial sodium batteries for years. The appeal is almost entirely economic and practical rather than exotic. Sodium-ion cells are expected to cost around 30% less than today's standard lithium iron phosphate batteries, largely because sodium is abundant and doesn't require the scarce minerals lithium mining depends on. They also retain roughly 90% of their capacity at -40 degrees Celsius, solving the cold weather range collapse that plagues conventional EV batteries in winter. The first mass-produced passenger vehicle to use the technology, the Chang'an Nevo A06, is expected to reach around 600 kilometers of range once the supply chain matures, and CATL's own chairman has projected sodium-ion could eventually take over 30 to 40% of the entire battery market. Not a niche product, but a genuine third pillar alongside lithium-ion and solid-state. The rest of the world is not just watching. None of this is happening in isolation. Ganfeng Lithium, the company behind those record-density solid-state cells, already holds supply deals with Tesla, Hyundai, BMW, and Volkswagen for the raw materials feeding this entire race, which means the breakthroughs happening in Chinese labs are already threaded into Western supply chains, whether those automakers set out to depend on them or not. Western and Japanese companies are running their own parallel programs on almost identical timelines. Mercedes-Benz drove a modified EQS fitted with solid-state cells for 1,205 kilometers on a single charge using batteries supplied by the American company Factorial Energy, which also has partnerships with Hyundai, Kia, and Stellantis, and recently launched its first solid-state program for passenger cars in the U.S. with Karma Automotive. Samsung SDI is promising an 80% charge in 9 minutes by 2027, and Toyota, BMW, Nissan, and Volkswagen are all targeting solid-state rollouts on a similar window. This is less a single country pulling ahead unnoticed and more a genuine global race where China currently holds the fastest lap times. How far this could actually go, and why it might not. It's worth being honest about how contested all of this still is because the industry itself is not in agreement. CATL, the company leading the entire battery sector, has repeatedly said that large-scale solid-state commercialization is unlikely before 2030, even as smaller, more aggressive rivals like Greater Bay push for 2026. One well-known industry expert, Ouyang Minggao, has predicted solid-state batteries will capture only about 1% of the market within a decade, a sharp contrast to the breathless tone of some of the announcements. And on the swap side, a battery supply chain executive named Davis Zhang has pointed out that it remains genuinely unclear whether millions of new cars will ever adopt swappable batteries, especially as ultra-fast charging technology keeps improving on its own. Some premium EVs can already add up to 500 kilometers of range in about 10 minutes of charging, closing the gap that swapping was built to solve. There are also real structural barriers. Battery swapping only works if automakers agree to standardize pack shapes and sizes, something most manufacturers have historically resisted because it limits design flexibility. Solid-state manufacturing requires entirely new production lines that cost billions to build, and every one of these technologies still needs years of real-world durability data before regulators and cautious buyers fully trust it. None of the companies involved are claiming otherwise. The mass production timelines being announced are pilot scale and early commercial, not yet the moment lithium-ion sedans get swapped out on every corner. What is different this time is that these are not lab demos anymore. Real cells are rolling off real production lines, real cars are already driving on sodium batteries, and a battery swap network has now completed over 100 million actual swaps for actual drivers. Whether any single one of these three approaches, solid state, swap, or sodium, ends up being the one that finally makes the gas station optional, is still an open question. But for the first time, it's a question with real vehicles on real roads, not just white papers. If this changed how you think about what's sitting under the hood of the next car you buy, like and subscribe for more on the technology quietly reshaping the world. And let me know in the comments, of these three approaches, which one do you think actually wins?